Bismillahirrahmanirrahim and Assalamu alaikum. Today we'll be talking about a very important topic in data structures and algorithm, that is Huffman encoding. Basically, it's a technique of compressing data to reduce its size without losing any of the details. Means to say that it will just reduce the size of the data without actually making any change in the specific data that is going to be compressed. So that is why it is actually known as a lossless data compression algorithm. It's a type of greedy algorithm that can be used for the encryption as well as the decryption of data as well. So it will be doing actually is to reduce the amount of space acquired by the characters for their storage. So basically, as we are going to talk about the data that can be encrypted or decrypted, so normally the data that we have or that exists is of three types. That can be text, that can be image, and that can be any of the video or audio. So these will basically be the applications of Huffman encoding that we'll be discussing at the end, that how we can use the Huffman encoding to encrypt or decrypt, basically how to compress all of these kinds in the through Huffman encoding. So the strategies basically used in the Huffman encoding, as we know that information in computer science is encoded in strings of zeros and ones. So in the first case, we'll be discussing about the fixed length encoding, in which every character is assigned a binary code of fixed number of bits. As one of the characters can be stored in 8 bits, that is fixed length encoding. On the other hand, the variable length encoding, opposed to fixed length encoding, uses a variable number of encoding bits characters depending on their frequency. So basically, the objective is to usually transmit the information using the fewest number of bits. So, moving towards the algorithm of Huffman encoding, that how we can use it. Basically, I've again divided it into certain steps so that we can clearly understand that how we can use it. Very first step is the arrangement of letters, that we have to arrange them according to the ones occurring most frequently. And then in the second step, we'll set up the frequencies, that how the letters in the sentence are occurring. We will write the frequencies of them with each other, and then we'll create a Huffman tree with that frequencies written, that we will take up to minimum frequency letters from the queue where we have written them, and then we'll add them, then we'll take another one, then again add them up till the root node. So that's how we will create a Huffman tree. In the fourth step, we will assign the bits to the nodes. Now it's up to us that what strategy we are going to use. If I am here, I'm giving zeros to the left ones and ones to the right ones, and in the very last step, we will multiply the calculated bits with their actual count, and then we'll add up all together so that we can get the compressed bits. So that is how we can use the Huffman encoding to encrypt or basically compress any kind of sentences, any kind of data. So here we'll take an example. Here we have given a sentence, choose to shine, and we'll try to compress this sentence. That will basically be a part of the text compression, that is going to be an application of the Huffman encoding. So in the very first step, we'll arrange the letters so that we can set up the frequencies, and then we'll assign the specific frequencies to each of the letters here. Now we will create a Huffman tree according to these frequencies written, that how all of the letters occur in the sentence, how many times. Now we'll start creating Huffman tree. So here we can see that the minimum of the letters here are T, C, N, and I, each having the frequency of 1. So we'll write it, and then we will add them all together. This will become 2, and here again it will become 2, and then we'll again add them, and it will result in 4, and we will remove the used frequencies from the instruction queue. Then we will take up another minimum, that is E, then we'll again add them, it becomes 6, and then we'll again take up the S1, or then I will be using H, that has 2 frequency, and at last I'll be using the O, and here is the resultant Huffman tree, in which these last ones are the leaf nodes and the starting one is the root node. Now we will assign the bits to the nodes according to the root node, so it is very much important. So here now I'll assign the bits to the nodes. Now it's up to us. Again, if we are giving zeros to the left nodes and ones to the right nodes, I'm using this strategy here. So I'll just quickly give the left nodes all the zeros and the right nodes all the ones. Now after this, I'll just calculate the bits of all the letters with respect to their root node. How much the all the letters are occurring according to their root nodes, and what will be their bit address. So for first of all, for the O, I can see that from the root node it has only one bit, that is 0, and its actual count was 3. So 1 multiplied 3 equals 3. Same procedure for all of the above. For H, I can see that it has 2 bits, 1 1, and its actual count is 4. For S, it was 3 and actual count was 2, so 3 into 2, 6. So that is how I'll calculate all of the letters and all of their bits. And after that, after multiplying all of them with their actual count, we will just simply add them all together. So here after that, add for the C, and then for the I, here I can see that it has almost 6 bits and its actual count was 1. And at the end, N has again 6 bits and its actual count is 1, so it also becomes 6. And T has also 6 bits, and at the end, C letter has also 6 bits, that are 1010000. So at the end, I'll just add up all them together so that I can get the compressed bits, the number of bits that we will have after the given sentence will be compressed. So adding up all together gives us 45, that are the compressed bits, the number of compressed bits. So now the very important factor that we have to look for is the compression ratio. So compression ratio basically is the ratio between actual and compressed bits. So how can we calculate it? As we can see that this sentence has the total letters 13, and as we know that each letter can have 8 bits for storage. So 13 into 8 becomes 104, and compressed bits were 45. So by calculating the compression ratio, that is compressed bits by actual bits into 100%, we get 43.26%. And this is a slight disadvantage of Huffman encoding, that we get a very low rate of compression ratio as compared to others. So moving towards the applications, as we have seen the text compression in the previous example as well. So moving toward the multimedia codecs applications, in the very first one is the image compression. So again, I have divided this whole process into certain steps so we can understand it quite easily. In the very first step, we have a digital image in any of the formats, JPG, PNG, JPEG formats. First of all, we will be doing its pre-processing. Pre-processing basically means to divide the or convert the image into pixels. For example, we have an 8 by 8 image and we will be converting it into pixels. So that is how we can see that which of the colors are repeating for how many times. From there we can get the frequencies of all the colors uh, repeating in the whole of the image, and then by using that frequencies we will do its encoding, that is to create a Huffman tree by using that frequencies that we have also discussed earlier. And that is how after forming the Huffman tree, multiplying all the numbers with their actual count and then adding them all together, we get the compressed image, that is the reduced image size, and at the output we will do having a reduction in the size without any other change in the formats of image. So the next application is the audio compression. Here again, it has 5 basic steps. In the first step, we will be having an audio file in MP3 format, in any kind of format. Uh, Again, we will be doing its pre-processing. Here, the pre-processing means to convert the audio file into the data transmission bit. And there will be two additions in the original codec. The first one will be PNS, that is perceptual noise substitution, and the second one will be the entropy coding. That is the same as Huffman coding, and we are using the Huffman coding actually to achieve the lossless compression in the audio file. So we'll just simply replace the frequently occurring symbols in the mantissa for each of the critical band with a code smaller than the original code. In this manner, we will reduce the number of transmitted bits, which gave us more compression of stored audio file. That means by generating a Huffman tree using the frequency symbols so that we can compress the given audio file, and the output we will be having is to have the same audio file with the reduced size. So this was all the Huffman encoding. Thank you so much.